Welcome to Case File 001. Today we are launching a deep investigation into one of the most significant shifts in the history of technology. We call it Agentic AI. You might be asking yourself why this is happening right now. Why are we suddenly seeing a move away from simple chatbots toward these complex autonomous systems? The answer lies in what we call as the perfect storm. This is not just a single breakthrough, but rather the convergence of three powerful waves that have hit the industry simultaneously. First, we have the brains, which refer to the massive leap in reasoning capabilities found in modern large language models. Second, we have the tools, which represent the new interfaces and protocols that allow these models to interact with external software. Finally, we have the necessity. Our modern world is becoming so complex and the volume data is so vast that human only workflows are starting to buckle under the pressure. As we peel back the layers of these investigation, we will look at how the fusion of these elements is creating a new category of intelligence. This is a top secret look into the architecture of future, where artificial intelligence moves out of the chat box and into the real world of production systems. Prepare yourself as we begin our investigation into the convergence of brain tools and necessity. Let us examine the narrative of the shift. In the past, we treated artificial intelligence like a collection of interns. Imagine running an engineering team where you suddenly hire 1,000 tireless interns. They are eager to help, but they require constant and highly specific instruction for every single task. For years, AI was confined to narrow roles like being a spell checker or simple ranking model. You gave it a prompt and it gave you a response. This was the era of the chatbot. But today, we are seeing a move from interns to operatives. We're no longer just giving these models one-off prompts. Instead, we are giving them high-level goals. We are treating them as autonomous members of a team. The evidence is clear. The core shift is that we provide a target objective and the agent determines the step to get there. The capability has expanded because we let them call tools and application programming interfaces instead of just answering with text. Finally, the integration is key. These agents are being wired directly into the production systems with constrained guardrails and feedback loops. They can read documentation, write code, and debug logs without a human holding their hand at every single step. This transition from passive assistant to active operative is the heart of the agentic revolution. To understand where we are going, we must first look at where we came from. We call this the old city, the era of narrow models. Historically, production machine learning was a series of disconnected silos. If you wanted a system to perform five different functions, you had to build five different models and find a way to glue them together. You had one specific model for detecting spam, another for ranking search results, and even a third for optical character recognition. Each of these required specialized training data and distinct engineering teams to maintain them. This led to a massive problem with fragility, which we have labeled Exhibit A here. The limitation was that each behavior was logged into a separate binary file. These narrow models could not generalize. A spam filter was brilliant at identifying junk mail, but it could not summarize a document to save its life. This created a rigid and expensive infrastructure that was difficult to scale. In contrast, modern systems use what we call as a general brain. A single large language model can provide multiple behaviors, including coding, reasoning, and summarizing. It does this through different prompts rather than different models. We have moved from a city of scattered sheds to a single central skyscraper that can house every function we need. Let us turn our attention to suspect number one, which is the brain. The real turning point occurred between the years 2020 and 2023. These models scaled in size, their behavior underwent a qualitative change. They stopped being just smart autocomplete system and started behaving like general problem solvers. This is supported by the scaling laws of neural activity. When we look at the evidence, we see that GPT-3 released in 2020 had approximately 175 billion parameters. This unlocked the ability for few shot and zero shot behavior, where the model could perform tasks it was explicitly trained for. However, the release of GPT-4 in 2023 with an estimated 1.8 trillion parameters brought about major jump in reasoning. We're now seeing key capabilities that were previously impossible. These brains can understand messy and unstructured inputs that would have crashed older systems. They can generate detailed step by step plans in natural language. Most importantly, they can adapt those plans on the fly when errors occur. This allows us to offload the heavy lifting of planning and decomposition to the model itself, making it the perfect cognitive engine for an autonomous agent. Despite the power of the brain, we found a significant flaw during our investigation. We call this Exhibit B, the limitation of action. Before the widespread use of tools, large language models were effectively brains without hands. We could ask them almost anything, and they would provide a fluent and highly intelligent answer. But they could not actually do anything. They were stuck inside a digital box. They could not query a database, execute a computer code, or modify the state of the system. This created a profile of a system that could talk but could not act. Imagine an AI that writes a perfect incident response plan for a server crash. If that AI cannot actually log into the server and run the commands to fix it, then it is not an agent. It is merely a consultant. In the world of high stakes operations, a consultant is not enough. We want systems that function as engineers. We need them to do the work, not just write about the work. This realization was a breaking point in our research. It highlighted that intelligence without the ability to exert influence on the environment is a stranded asset. To solve this, we needed to find a way to give the brain hands so it could move from providing advice to providing solutions. This leads us to a suspect number two, which we call the hands. To transform from a consultant to an engineer, the brain needed a way to touch the physical and digital world. This was achieved through function calling and API integration. This is the mechanical integration shown in our Exhibit C. Function calling allows the large language model to select a specific tool like a weather service or a database query and generate a structured call. This is the mechanism of action. The process starts with a trigger where a model chooses a tool and outputs a JSON object. It is important to note here that the model itself does not execute the tool. Instead, the runtime environment receives the request and performs the action. This creates a powerful loop. First, a user asks a question. Second, the brain selects the appropriate tool and the necessary arguments. Third, the runtime executes the tool and retrieves the data. Finally, the brain incorporates that new data into its final answer. By giving the brain these mechanical hands, we allow it to interact with the world in a structured and predictable way. It can now turn a wrench or pull a lever in the digital space, which is the fundamental requirement for any truly agentic system. Now we'll look at the operational blueprint to see how these hands actually operate in the field. Modern agents do not just follow a hard-coded script like the simple programs of the past. Instead, they use dynamic tool selection. An agent can look at the error message and decide whether it needs to fetch logs, restart a service, or escalate the issue to a human supervisor. It chains these tools together in sequences that were never explicitly pre-programmed by a developer. This is shown in Exhibit D. The technical specification involve schema-based prompting where the entire toolbox of the agent is defined using JSON or OpenAI schemas. This gives the brain a map of what it is capable of doing. We also see a pattern of chaining where the output of one tool becomes the input of the next command. For example, an agent might find a server ID with one tool and then use that ID to issue a restart command with another. This design pattern is critical because it separates the decision making process of the brain from the execution process of the runtime. This separation allows for a greater safety and flexibility as the brain can reason about the best path forward, while the runtime ensures that the actions are performed correctly within the system constraints. Now, every investigation needs a motive, and for agentic AI, the motive is a suspect number three, which is the combination of complexity, volume, and demand. We have the brain and we have the hands, but the real catalyst is the overall overwhelming pressure of modern systems. We have reached a breaking point in Exhibit E. Our digital environments are not now characterized by multi cloud architecture, global telemetry, and the need for 24/7 operations. These systems produce an exponential growth in data, which is simply too complex for human only workflows to manage. Manual handling of these alerts is becoming expensive, slow, and prone to errors. Human cannot keep up with the sheer volume of logs and metrics flowing through the pipelines. This is where the economic factors come in. Report indicates that organization can see a 30 to 60% cost reduction in operations by using agentic use cases. We see efficiency gains of 20 to 35% across various sectors and accuracy rates of over 95% in areas like fraud detection. Autonomy is no longer a luxury or a research project. It has become a survival necessity for businesses that want to scale without being buried under the weight of their own operational data. Let us look at our first case file, which we call as the researcher. This focuses on cognitive work and information synthesis. Agents excel at information-rich tasks that require multi-step reasoning. Unlike a simple chatbot that just retrieves text, a research agent can search, filter, cross-check, and synthesize data from multiple sources simultaneously. It can reach into CRMs, analytical platforms, and ticketing tools to produce a coherent output. As we see here in the Exhibit A, the multi-armed researcher is a powerful entity. The primary use case here is for knowledge worker assistance. The key differentiation is that this requires true synthesis rather than just simple retrieval. An agent just does not give you a link. It pulls data from the dynamic API, summarizes large set of documents, and drafts a comprehensive report without any human intervention. This capability transforms how we handle business intelligence and market research. Instead of a person spending hours clicking through different dashboards and copying data into a spreadsheet, the agent does the legwork in seconds. It understands the context of requests and knows which sources to trust and how to reconcile conflicting information. This is the future of knowledge work, where AI acts as a high level analyst. Our second case file focuses on the fixer, which deals with operational automation and incident response. In the world of operation, latency and uptime are the most critical metrics. When a server goes down, every second counts. Agents are now being used to handle incident response, supply chain orchestration, and customer service automation. They act as the first line of defense in a digital infrastructure. As shown here in Exhibit B, the unflappable operator can handle a crisis with calm and precision. The benefit is high speed remediation, which directly reduces downtime and saves revenue. However, this power must be controlled. This is why the agent operates within strictly defined guardrails to ensure safety. For instance, a guardrail might be a hard rule that says the agent is never allowed to delete a production database. These constraints allow the agent to move fast and fix problems while preventing catastrophic mistakes. The fixer can monitor metrics and logs in real time and take action the moment a threshold is crossed. If the problem is too complex, the agent can prepare a detailed brief and escalate it to a human engineer. This collaborative approach ensures that the system is always being watched and maintained even when the human team is asleep. To make this concrete, let us walk through a reconstruction of an incident response scenario. Imagine a production incident where an alert is triggered in the middle of the night. In the old world, a human would have to be woken up and start digging through logs. In the agentic world, the large language model is already on the job. It's not just summarizing the alert, it is actively choosing diagnostic tools, interpreting the results, and triggering remediation. Step 1 involves ingesting the alert and the messy logs associated with it. Step 2 is where the agent decides on the diagnostic tool to use. This is the dynamic selection based on the specific nature of the error. In step 3, the agent proposes a remediation plan, such as performing a rollback to a previous version or restarting a specific microservice. Finally, in step 4, the agent executes the action if it is authorized to do so, or it requests human approval if the action is high risk. This sequence from alert to resolution is shown in this reconstruction diagram. We move from a red light of a problem through diagnosis and planning to the green light of a resolution. This is how the brain and the hand works together to solve real-world problem in record time with minimal human friction. We have reached the end of our investigation and the verdict is clear. Case closed. Agentic AI is inevitable. When we ask why this is happening now, the answer is the perfect storm created by convergence of three waves. We finally have a general brain capable of high-level reasoning. We have the hands through function calling and APIs that give the brain the power to act. And we live in a world so complex that it demands autonomous help just to keep functioning. Agentic AI represents the moment where capability meets necessity. As we look at the final summary, we see that the brain provides the planning, the hand provides the execution, and the demand provides the motive. This is not just a trend, but the only viable path forward for the next generation of software. The future belongs to systems that can think and act on our behalf. We are moving towards a world where technology is no longer a passive tool, but an active partner in our success. Our investigation has shown that the components are all in place and the integration is happening as we speak. This concludes case file 001 on the rise of agentic AI. The future is no longer a secret. It is a reality that we are building today. Thank you for following this investigation into the perfect storm. If you like my video, please do not forget to like, share, and subscribe. Thank you.